Okay. Well, we had some homework due today on Leibniz as an axiom, and I think we also had a monotonicity proof.
I have a question.
Sure. What's your question?
Okay. This is
For which one are we? Which?
It's actually just a general question.
Oh, a general question. Okay.
Okay. On any of the one where you're doing
Leibniz?
excuse me, as an axiom.
Yes.
Whenever you are doing textual substitution, do you like on 3.5a, for example?
On 3.85a, yeah.
I mean, this one I could solve without doing it, but just using it as an example. Like, if you substituted something for p, do you also substitute it for that in the e to the?
Yes. Yes, you must.
Okay.
The p, yeah. So the question was with 3.85a, when you do textual substitution, you say p replaced by something. Then if you're going to replace this p by something, then you got to replace this p by that, and you got to replace this p by the same thing.
Wait, I didn't replace anything.
This e superscript z subscript p means e was z replaced by p. The question is, if you use a previous theorem, or like if you're going to use 3.85a, and you're going to use it with a textual substitution, if you do it with this p, you got to do it with this p and with this p. Yeah, yeah.
Sense. You can use 385A to solve 385B, right?
Yes, once you prove 3.85a, you can use it in your proof of 3.85b.
Is that how you prove it?
Oh, that's not how I, well.
I proved it in one step. I just want to know if that's right.
Okay. But it doesn't really.
Probably not.
Whoa, 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 whoa. In one step?
Yeah. I replaced P with Q and P.
Yeah, but no, you can't do this in one step, because the problem is if you're going to replace, and here, if you're going to put P and Q here, it's this, you can't do that because this P would have to be P and Q and P also. So that didn't work.
Why doesn't it switch that too?
It's just P on the bottom one. See that?
You can't.
Look, if you here, 3.85b with P replaced by P and Q is this. It's P and Q implies E with Z replaced by P and Q equivales P and Q.
That second P and Q is an N, or B, so you can't be, at least you're not done.
Hold on. P and Q implies E with Z replaced by true. What I'm saying is 3.85b with this is this.
Yeah.
Yeah, but then you have this P and Q here, but didn't I do that right?
That's right.
Everywhere there's a P in 3.84. Oh, sorry. This is 3.85a.
Okay, we're good.
Yeah, yeah. 3.85a with P replaced by P and Q is this. And I don't think this helps you to solve 3.85b. See, because if you're going to substitute, actually that was your general. This is an example of your general question.
Right. Yeah, that's what I was asking.
Yeah, yeah. So no, I mean that's.
Can you not just replace the first P?
No. Anytime you do textual substitution on the whole thing, you got to do textual substitution with every occurrence of that.
But that's what we did when we solved 3.3.
No. We have never. I guarantee you, we have never just replaced one of the P's and not all.
That's substituting equals for equals.
Oh yeah. Oh, good point. Substituting equal. Yeah. Don't confuse textual substitution with substituting equals for equals.
So on 385b,
Mm-hmm.
could we have a first step / general direction that is?
Oh, you want me to give you a hint on how to solve 3.8, on how to prove 3.85b?
That's right. I just pulled 5 rabbits.
Okay. Well, actually,
How about A?
yeah, you want a hint on how to.
Just hit me on all of them.
You just hit me on all of them. Just do them for you. I don't think so. Okay. Okay, let me give you a hint on 3.85. 3.858, what I suggest you do is you start with the left-hand side, all right, and you pull a little rabbit out of a hat
On A or B?
on A.
Oh.
I'm talking about proving 3.85A. Because look, what does 3.85A look like? I mean, we have to get,
It looks like
I don't get why you said to
that
see.
P implies P equivalent is true.
On that one though, I think it's a lot simpler if you pull out P, if you solve the entire thing and head back to 3.83.
Whoa.
383. I don't think you want to head for 383. I think you want to head for,
Well, it works apparently.
oh, maybe it does. Maybe it does. But the hint I was going to say is I was thinking about 3.84B.
What? I thought we were talking about, oh, 3.83.
No, I would get it to 3.84B.
How do you do that?
Well, I'd pull a rabbit out of a hat.
You do how I saw
You just-
3.85.
I would, okay, hold on. No, I didn't say, look, we just explained what pulling a rabbit out of a hat is, and sometimes you have to resort to pulling a rabbit out of a hat. I mean, that's how we solved De Morgan B, right? We replaced P with not P. That was pulling a rabbit out of a hat, but that enabled us to do a short proof. Well, you can do it an infinite number of ways. I'm just saying how I would do it.
That's how I saw 3.85.
Alright, which rabbit should I pull?
Okay, you want me to give you a hint on a rabbit?
Give me the rabbit.
Yeah, I give you the rabbit. All right. What I would do is, look, do you see that 3.85A is very similar to 3.84B?
Not at all.
What do you mean not at all?
P with E.
You have something implies an expression with Z replaced by E, equivales something implies an expression, right?
But you said to start with just the left hand side.
No, I was talking about,
B himself.
What are you talking
well,
about?
no. Yeah. Start with the left-hand side. You can start with the left-hand side. But what I'm saying is, I would start with the left-hand side, and what I would do is I would use the identity of equivales. Because you know equals and equivales have the same.
Yeah. Oh. Yes.
And so look,
P
here
equals true.
P equals true, because not only that, because what will happen is the
Yeah.
F will be true, right?
Yeah.
And then you've got this true down
Drop
here.
P, the true later on.
Yeah.
How do you do that?
He sees it.
I got it.
Did you hear that?
No, I'm seeing if Crowley's right, but it might not be. So.
Okay, what I'm suggesting is start with the left-hand side of 3.85A, and the rabbit you pull out of a hat is you say P implies E was replaced by P equals by, what's the identity of equivales? Which one is that? 3 point, no, that was a real early one. It was real.
3.3.
Oh, that's what
Oh.
you did.
Change that to P equals true implies E was replaced by
See,
P.
that's what you did. So that was the right
So
way.
why did you say on the website to use 3.76?
Oh, is that what I said?
Right.
Oh, I didn't realize that. I was just looking at this. Oh, I did not realize that I gave a different hint on the website.
So my question is actually about part B though.
Okay, so you want to prove 3.85B? Yeah, I have another hint for that. For 3.85B.
Did you get it?
More rabbits?
I would start with the left-hand side again. And what we have is Q and P implies E was Z replaced by P, right? Here's your hint. Here's your hint. Are you ready?
Nope.
True.
Shunting.
Okay.
It works for 85B.
Yeah.
You have one more step and you change it equals. But yeah, that works.
Oh.
You know when you when you use that 3.3, the identity to just pull the true out of the hat,
Mm-hmm.
and you doing it with just equals rather than equivales?
Yeah.
Do you need to write anything saying?
No, you can quote the same, it's the same thing, because equals and equivales have the same truth table. I mean, they have the same truth table, so it applies to equals just like it applies to equivales. No, you can just quote it.
All right.
This might not work. She has a way to do the A. And I'm curious.
So you have a different way to do A. I'm sure,
It's the same way, but you use use the whole thing, and then you first do the one where the
Distribution of
P equivalent, or P implies E, with P replaced by Z equivales E with true replaced by Z. And then you would do the
3.3.
3.3,
which is like.
which is,
Yeah, well, if you start with the whole thing, that's fine. That's just a different style of doing the
How
same
many
thing.
steps is that?
was
Yeah.
also what he said.
2.
yeah.
That's a good way to do it.
You see that? That's nice.
I was changing equals to equals sometimes.
Yeah. You have
Okay, are we good?
to-
Isn't this stuff cool?
A lot of rabbits just hopping around.
Yeah, the same way these chairs multiply in the room overnight. We have all these, too many chairs in this room.
Focus on
They're like rabbits, they multiply.
The chairs are everywhere.
Okay, any more questions about the homework?
We can turn it in by 5.
Yeah, the question is, can you turn it in by 5? The answer is yes, as always. But see, the whole idea is that you have tried the homework
Yeah.
and you come to here with questions. It's not that you come here not having tried the homework,
Yeah.
and then you listen to how what everybody, and then you go and get it done by 5. I mean, that's a little that's not the intended outcome of the policy. Although, like many things, policies have unintended consequences. Okay. Well, so are we good for proving 4.1? And how about the monotonicity one?
That one was easy.
That one was good?
I had difficulties with.
Okay. Wait, did you say you have another question?
I didn't really have a question for it. I just didn't really know where to start on that one.
On which one? 4.3? You didn't know where to start on?
No, 4.3 was easy.
Oh, 4.3 was easy. Which one? The 4.1?
Hot, like, follows from.
Oh.
See, I started with the right,
Yeah, start with the right-hand side.
and then you make it where it follows from P.
Yes.
Okay.
Yeah. So 4.1, the hint is to start with the right-hand side and get it to follow from P.
You can do 76A with like anything.
Actually, it's just a two-stepper.
Otherwise, it's-
Who is your friend?
It's not Q.
Yeah, 3.59.
Yeah.
Sorry, I got it.
Yeah.
At least I got
You're writing down all the hints? He's fishing for hints. One other hint. Okay, are we good to go? All right. Okay, so before we continue on with these proof techniques, I would like to emphasize something that I mentioned in class last time. And that is, we are learning in Chapter 4, we are learning these proof techniques, starting with 4.4. So these proof techniques to be legitimate, it's only okay to use these proof techniques after Chapter 4. It's only okay to use these proof techniques after Chapter 4, because you have to you have
If you
to
prove something before that, then you
yeah. Okay, so we're going to introduce this concept of what I call a reproof. Okay, and I just want to make sure that everybody understands what we're doing here. Because they make good exercises, because they make good exercises, we will illustrate the proof techniques. We will illustrate the proof techniques by reproving previous theorems. By reproving previous theorems, all right? These are not really legitimate proofs. They're just good exercises, okay? I just want you to know that. I want to make sure everyone knows that. Okay, I just wanted to emphasize that fact. Because we're going back, we're using a proof technique from later to go back and prove, so like if we were going through and proving that an earlier proof, we would not have gotten to chapter 4 yet, so we can't jump ahead and use that technique to go back. But anyway, it's just, I thought about, tried to come up with examples and it's just, this is just the way we're going to do it. It's just too hard to come up with examples. I need a good set of, you need a good set of examples to do it. But going forward, when we have new theorems, of course, all the theorems that we prove later using these techniques, of course, are legitimate proofs. Okay, I mean are legitimate because from now on we have gotten past chapter 4.
Yeah, because you can prove all the ones before this without using these techniques.
Yes, yes, you can prove all the ones before chapter 4 without using these techniques. Okay. Now, the next technique that we are going to use is called case analysis. So let's take a look at, this is proof by case analysis. And before we take a look at proof by case analysis, what I'd like for us to do is to go back and take a look at these Leibniz's and axiom theorems, because proof by case analysis is actually based on them. And so there's some really interesting ones here. I don't know if you've thought about some of these yet, but just check out particularly let's take a look at 3.87, 3.88, and 3.89. Now, 3.87 says replace by true. I want to see if I can convince you why that is a reasonable theorem. What it says is that P and E with Z replaced by P is equivalent to P and E with Z replaced by true. Does that make sense? Because, well, when you say P and this, you're saying P is true and E was replaced by P is true, right? But if you're saying P is true, then E was replaced by P has to be the same as E was replaced by true. Yeah. I'm just trying to get you to feel what it says. Yeah. Now this next one is a little bit trickier, because this one says P or E was replaced by P is equivalent to P or E was replaced by false.
Yeah, because if you threw a false on there, if P was true, it'd be true anyway.
Yeah, well, if P were false, then P or E was replaced by P would be E was replaced by... Yeah. Well, see, what is false or anything?
Anything.
That's the anything, yeah. False or whatever is whatever, yeah. And then Shannon is kind of related to that in a very interesting way, because Shannon says E was replaced by P is equivalent to P and E was replaced by true, see that's this one, or not P and E was replaced by false. So it's kind of like combining 3.87 and 3.88 in a certain way. Now I haven't asked you to prove these, and these aren't on... Yeah, it would be nice if I just had you prove them all, but we don't have enough time. But these are all provable in the same way that you've proved these others. And in particular, 3.89 Shannon is the basis for what we call case analysis. So here, let's jump ahead. Let's jump back here to see what case analysis is. Case analysis is 4.5. It says, if E was Z replaced by true and E was Z replaced by false are theorems, then so is E was Z replaced by P. That's odd. And so what case analysis says that we can do is, to prove a theorem, we can break it up into two parts.
Yeah.
We can break it up into two parts. First of all, we can prove E was Z replaced by true. And if we can prove that on the one hand, and then on the other hand, also take E was Z replaced by false and prove that one, then since P can only have two values, either true or false, then E was Z replaced by P must be true in all instances, because if it's true when P is true, and if it's true when P is false, then it's true for P in general. So basically what we do is we divide, in case analysis, you basically have two sub-proofs. All right? Now here, so let's go back here to, oops, wrong direction. So let's go here to Shannon, and I want to show you, this is kind of strange. I want to show you why Shannon allows us to do case analysis, because look at what this says. It says E was Z replaced by P. That's what we want, right? This is what we want to prove, right? E was Z replaced by P. That says that equivalents P and E was Z replaced by true, or not P and E was Z replaced by false. So why, here's the question. Why does Shannon 3.89 justify proof by case analysis? Why does Shannon 3.89 justify proof by case analysis? By the way, this is not in the book. I had students ask me, well, how does that follow? And it's always been a little bit of a puzzle. So I want to show you here why this works. So what we're going to do, here's what we're going to do. We're going to do, what I want to show you is what Shannon says in the event that you can prove both E was Z replaced by true and you can prove E was Z replaced by false. Okay, so let me just write down Shannon. E was Z replaced by P equivalents P and E was Z replaced by true, or, and here's what's puzzling. It's this or, and not P and E was Z replaced by false. Because, after all, what we have to prove is E was Z replaced by true, and we have to prove that E was Z replaced by false. So why isn't this an and instead of an or? That's what's a little puzzling, but I want to show you how this works, okay? So here's the thing. Suppose that we are doing this by case, suppose that we do our proof by case analysis, and we actually prove that E was Z replaced by true is true, and we also prove that E was Z replaced by false is true, okay? So here, what I'm going to say is here is prove, if you prove by case analysis E was Z replaced by true and E was Z replaced by false. So if you show that both this and this are true, what do you have? You have E was Z replaced by P equivalents, now watch what you have, P and true. Are you with me? Because we did this part by case analysis, yeah? Or not P and we also proved this part by case analysis, right?
Okay, how did you prove by case analysis?
Well, assuming that you've done that. I'll give you an example and show you how to do that. But in proof by case analysis, let's say that you've done a proof by case analysis and you have shown that those two parts are true, okay? If that's the case, then what have you done? You've shown this, P and true, right? But look, you guys, what do you see right away? What do you know right away when you have something and true?
True.
Is that what you have?
Yeah.
You have true? Is P and true true?
P and true is P.
Yeah, what is it? Which one is P and true?
P.
Is it true or is it P?
P.
Well, now come on. Oh, we need to review. We need to get this one down. Is it true? Wait. What P or true? Hold on. Hold on. Hey, here we've got P and true. We have P and false. We have P or true. We have P or false. These we better know by now, I hope. So what do we have? P and true. Which one was P and true? Which one was that? This one's P, right? Not true. Okay. And what about P and false? This one's false. This is a zero theorem, right? Okay. And this one is what? P or true is what? This one's true. This is also a zero theorem. And what about P or false? This one's P. Okay? Yeah, these are identity. This is an identity theorem and this is an identity theorem. True is the identity for P, false is the identity for OR. Yeah? Okay, so just jog the memory there. All right. So this is, but what do we have here? P and we have a conjunction with true, right? So that's the, what is this? We're using the identity of conjunction, right? So this gives us E was Z replaced by P equivales, and what do we have? What do we have? P and true is what? Hello? Testing. 1, 2, 3. Is the mic on? You can cut that corny joke. Okay. Yeah, this P and true is P. Yeah, and this not P and true is not P. So what do we have? P or not P, which by excluded middle. So this equals by excluded middle. This is the same as E with Z replaced by P equivales true, right? And that's exactly what we're saying. If you do each one of these individually by case analysis, basically what you're showing is that E with Z replaced by P is true.
This is a reproof, right?
No. This is not a reproof. This is a demonstration about why Shannon is the basis for proof by case analysis. Shannon shows that proof by case analysis works. Do you see what I mean? Because what it says is that if you can prove this is true on the one hand, and you can also prove that this is true on the other hand, this demonstrates that you are showing E with Z replaced by P is true in the general case, no matter what P is. Do you see what I mean? And this actually shows specifically why case analysis. This is the theoretical justification for proof by case analysis. So now, after talking all about this theory of case, let's actually do a couple of proofs by case analysis. Okay. So here's an example. Let's reprove 3.80. Let's go back up here. Do 3.80. So what is 3.80? We're going to reprove 3.80 mutual implication. Reprove 3.80 mutual. So we're going to reprove 3.80. A mutual implication. Now, what does mutual implication say? And It says P implies Q and Q implies P equivals Q. Now, anytime you do a proof by case analysis, you have to pick your variable. And here's what you have to say. We're going to say, by case analysis on P. Because look, this has two variables, right? 3.80 has a P and a Q. So here's what you have to say when you do proof by case analysis. I insist that you say this. By case analysis on P. You have to say which variable you are doing your case analysis on. Okay? And after you say by case analysis on P, then what you need to do is write down the Boolean expression that you are trying to prove in the two cases. One where P is true and one where P is false. And the way you do that is you number them. 1. So let's write down 3.80 with P replaced by true. So what is 3.80 with somebody tell me what to write down. If write down 3.80 with P replaced by 2. What do you have? True implies Q and Q implies true equivals true equivals Q. Okay, that's 1. And the second thing you have to write down is the same thing, but everywhere there's a P, everywhere that you replace it by false. Okay? So now let's write this down with false. So what do we have if
False implies Q.
false implies Q
And Q implies false.
and Q implies false equivals false equivals Q. Okay? And now you prove each one of these separately. And you can prove each one of these separately using whatever technique you want. Okay? So we say proof of 1. And then we'll do a proof of 2. We have to do 2 subproofs. So how would you prove 1? If I said prove this, and just gave you this as the first one is what's the first thing you'd look? Actually, it's well, yeah, but how would you prove it?
You get one side to the other.
You could get one side to the other. Let me think. How would you manipulate? Which side would you start with?
The left side.
Maybe start with the left side, and how would this pan out? True implies Q. Do we have a theorem for this? Do we have a way to manipulate true implies Q? Well, come on. Don't make me do all the work. Yeah, come on. So what do we have?
True implies P equals P, so true implies Q equals.
So this would be a Q, and then what would this would be?
True.
Oh. So then we would have a Q and a true, and what would that be?
True.
Q.
It's Q.
And what we would, which we can, I think we can do it, easy. All right, so you want to start with the left-hand side then?
Yeah.
Okay, so let's do true, well, we can do the whole thing. Or the whole thing.
Then you end up with 3.3. Yeah.
Okay, you want to start with the whole thing? Okay. True implies Q and Q implies true equivals Q. And this equals, and let's use both of those at once. I mean, are we good enough to where, which theorem was this one?
That's 3.72. No, wait, 3.73. Left identity.
Is somebody checking us on this? I want to get a 3.73?
Yeah.
And so we'll do that one on this, and then what was this one?
3.72.
This one's 3.72. So we'll do 2 steps at once, right? Because we're getting pretty good at this stuff. And so this is what? Q and true. Q and true equivales true equivales Q. And we did a remove unnecessary parentheses, right? But now what's Q and true?
Q.
And which one, which
Identity.
identity of and?
We don't have to know the number as long as we know.
You know what? That's the nice thing about the ones that have names that you can remember. It's at this point you should be able to remember the names and you don't have to quote the number. So that's a big help. Yeah, we can just say identity of, or you can go back and look it up and put the number if you want. But shoot, if you know the name of the law, boom. Shoot. So this is what?
Q equals true equals Q.
Q equivals true equivals Q. And now we can just say what?
By symmetry, it's
Well, we can just say more than that. Say it again. Which is 3.3, isn't it?
So for the case analysis, you have to do 2 proofs.
well, it's 3.3 with symmetry.
Well, symmetry, yeah, but we can do that in our head. Yeah. Yes, you have to do 2. You have to do. So now what do we have? We're not done.
So you can just do 1.
Because it might be the only way to do it.
Well, I mean, it might. Well, look how easy it is. I mean, some people. Here's what happened. One year I had this guy who said, "Whoa, proof by case analysis," because it's these ones are, even though it's longer. You have these trues and falses. You have these constants with trues and falses, and usually those things fall out really easy.
Okay.
You know what I mean?
Okay.
And so the guy went hog wild, and all of a sudden everything was proof by case. And so finally I had to put a stop to it. And so,
Right.
so I'm going to have a rule. Here's the rule.
I don't like rules.
You don't like rules? My rule is I'm only going to allow you to use proof by case analysis if I tell you that I want you to do proof by case analysis. Otherwise, I don't want you to use proof by case
You don't want
analysis.
us to do any of that stuff on the homework, right?
Well, I mean, the next homework is going to be proof by case analysis. But wait a minute, we're not done yet.
Do you want us to use mode for simplicity or anything?
What?
The last homework?
The last homework the ones due today?
Okay. Never mind, don't worry about it.
Never mind? Okay. Good. I will never mind. Okay, so now let's think about 2. How would we do 2? Maybe the same kind of thing?
Exactly.
You want to start with the left-hand side? Do you want to start with the left-hand side?
Sure.
So what is it? False? Somebody read that for me. Equivals?
Whatever.
Come on, what do you mean whatever? Equivals implies whatever. Equivals is not quite the same thing as implies. False implies Q what?
And Q implies false, equivales false,
Was this an and?
and Q implies false, equivales false.
Well, you want to start with the left-hand side?
Doesn't really, it's easy.
So do we have some theorems for this?
So that's going to be true.
Which, can you give me a theorem number?
75.
3 point?
It's all in 3.
3.75. Will that take care of this? Well, what takes care of this one?
74.
So what is this going to be? True and not Q, which equals by identity of, oh, I see why you wanted to start with the whole thing. Yeah, do it the same way we did that one. Identity of and, this is going to be what? Not Q, equals by 3.3, what is it we're trying to get it to? Oh, wait, not 3.3. No, I don't think you do. Ooh, how are we going to get this? How are we? No, I don't think we can just start with the whole thing.
Q equivals false.
3.15 is what?
Not P equals false.
Yeah, so 3.15, so that's going to be what?
Q
Equals false.
Q equals false.
The other side.
We got it to the other side. We used two different styles here. We could have done the whole thing here, but whatever.
This is way simpler.
Starting with the whole thing is way simpler?
Yeah, you know what you do is you stay here, and on Saturday you have this job, you go to a concert.
Ooh, you don't have class.
Well, we don't have class, there's no classes tomorrow at all because of this conference, faculty conference, but fortunately, we never have class on Friday
My
anyway.
accounting teacher this evening canceled our class as well.
Today, she was like,
What do you even do with these conferences? So after we prove 1 and 2, we don't have to go back
And say
Well, I have a twin one.
do we have to go back to the bigger proof?
proof, no, and the answer is no. Okay, the question is, after you finish the second one, do you have to go back and make a statement? And the answer is no, because you started the whole thing by saying proof by case analysis on P, and then you wrote down 1 and 2. So once you prove 2, you've already set it up.
Okay.
So you don't have to say anything more,
Okay.
because you set it up, because of the way you set it up. But you have to set it up, proof by case analysis on whatever in fact, it might be an interesting exercise to do this by proof. You could do proof by case analysis on Q.
Say hi to
You just need to pick one variable and then do case analysis.
Yeah.
And then you're done.
Yeah.
No.
That is only if you have 2 variables.
No, if you have any number.
So if you have like 10 variables.
If you have 10 variables, you pick
then do
one.
case analysis?
Yeah.
Now, this
That wouldn't work as well, I don't
That's
think.
counterintuitive.
this all is assuming that the 2 cases that you're proving are exhaustive in the entire space.
But look, in Boolean, the only constants the reason this works is because the only values that a variable can take are true and false, because those are the 2 constants in Boolean
What about
expressions.
something like this? 355.
355? Okay, hold on.
P isn't directly like say, because you have like Q or R.
Yeah, you could prove 3.55. You could do proof by case analysis on any one of those variables. 3.55, yeah.
That's weird.
So like you could do it, if you did it on Q, it would be P and false and R equals, and so on. And then you'd have then do another one. Actually, here's another thing.
Isn't case analysis basically doing truth table?
Well, actually, let's think, okay, since you brought that up,
it reminds me of it kind of a lot.
it not only does it remind you of it, but think about this.
It is.
Suppose that we wanted to do proof by case analysis of this one that we just did, and we said 1, prove this, with P true, 2, prove this, right? And then suppose when we wrote down 1, we said prove by case analysis on Q. And then you would have a 1A, and then you would have a 1A, and you would have a 1B. And then if you did 2, you would say prove by case analysis on Q, and then you would have a 2A and a 2B. Now think about what you're doing here. Every single thing would be all trues and falses. There'd be no variables left. So you would be, in essence, doing the truth table. So if you do a case analysis, and each one is done by case analysis on the other variable, and if you had that 3 point...
Wait. Why do you have A and B? I missed it.
It's the 1 and 2.
It's the one, when we did 1, we were proving a theorem that only had a Q in it.
Oh, okay.
So if you wanted to do that by case analysis on Q, and you would have 2 proofs in there, right? And then if you did 2 proof by case analysis, you'd have 2 proofs in there, right?
What's the 2 though? What's the difference between 2?
Well, remember we had this whole thing was proof by case analysis on P.
And so we
Prove
I'm lost as to why there's 4 different proofs.
We had when P was true and when P was false, and now he's saying, well, now you can do it when P is true and Q is true, and then when P is true and Q is false, and then when P is false and Q is true and P is false and Q is false.
Yeah, and those, in fact, are, see, when you did a truth table, true, 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 false,
Oh, yeah.
Wait, how's
False,
that
true.
case analysis on P? Isn't it, where, you say case
What I'm saying is
Q
the-
and case analysis on Q.
what I'm,
Isn't one of them supposed to be P?
no, the whole thing is on P.
Yeah, but you haven't tested P anywhere. Like you said, prove by case analysis.
Analysis on P. No, hold on. We say prove by case analysis on P, and then we wrote down what we and one we wrote down an expression that only had a Q in it, and for 2 we wrote down another expression that only had a Q in it,
And it had trues and false.
and it had true. This one had. Are you with me?
No, I'm
You're,
completely lost.
It would work better if we wrote it out again, but.
yeah, I erased it. Well, here it would be like this. Here, let's come over here. Suppose instead of proving this way, now you finally got it. It
Do
clicked.
case analysis on the
On the case analysis, exactly.
and then you just have false and true.
And basically then is, and in fact, look what you have. You have 4. This is the one where you're proving it with
True and true.
true, true,
True and false.
true, false,
False.
false, true, false, false. You're basically doing proof by truth tables.
We're not doing truth tables again, basically.
Well, that's why I say proof by case analysis is kind of cheating a little bit because,
That's why you don't want us to use this solve.
yeah, I mean, because basically here's what you could do. Here's what you could do. You could always use proof by case analysis on the case analysis to do everything with the truth table. And we said, no, we're done with truth
It's
tables.
frowned upon because if you have 4 variables, that's 2 to the 4th power cases.
Yeah, it'd be
It's just a
16.
huge proof.
It's a huge, I know, and huge in T,
It's like cheating. It's like a last resort.
it's a brute force. It's a brute force thing.
If you have n variables, that's 2 to the
The
n.
n-
It's very
Yeah. And besides that, you lose. The other thing we said, that we called that the combinational explosion. That's one reason we don't do truth tables. The other thing is, you lose sight of the structure of the relationships between the theorems. You know, it doesn't provide insight. Whereas if we understand the properties, that gives us insight as to the structure of predicate
With
calculus.
case analysis, you don't really need any of those theorems. If you just keep doing
If you did exactly, you would not need. Is all you would need to do would be to, you would have to do the previous, because you'd have to say true implies false. You would need,
identities and
you would. Yeah. But once you had those rules down, you know.
Well, if you exhausted it, there would be no variables. So then it's just the definition.
if you just go down to true,
Of the operators.
implies false and false.
Yeah, is all you would need. Yeah.
You just need the definition of the operators.
Right. Okay, so anyway, I was going to do another example, but I was going to reprove 3.42 contradiction, which is kind of neat.
We've got 1.5 minutes.
Do it.
Do you think we should try?
Do it.
He's egging me on. Oh, I don't know.
Reprove it by case analysis?
Just be halfway over again and just hang over all weekend.
Yes.
I was trying to do last time. I just.
You were hanging. You were going to bed at night thinking, "Oh, what's going to happen on that last step?" It was. Okay, let me just put it down. I won't do it. Reprove 3.42 contradiction. Reprove 3.42 contradiction. By case, I think this one is just a P.
Yeah.
Okay, so by case analysis on P. And so what are the two ones? Let's look at 3.42. Actually, we can do this pretty quick actually.
True and not true is false, and false and not false is
3.42. P and not P equivals false. So that would be true and not true equivals false. And the other thing is what?
False and not false is false.
False and not false equivals false. So notice how we number them like this, okay? And then proof of 1. Let's start with the left-hand side. What is true and not true? How can we prove this?
Well, it's
Equals by something with something replaced by something. But you know, by the way, even though we're doing this, we can't use anything after 3.42, you know.
Sure. Anything and, okay, well, not true is false by,
Well, can't we have the identity? I mean, here we have a true and.
right,
So
it's the identity of.
identity of and.
and. I should
Identity.
do it in a different order, because then you get not.
Oh, I see. Okay. So this is not true.
And that's
But
the
this equals by what?
definition of false.
Which number is that?
3.8.
3.8. False. Okay, and we've done that one, right? Okay, and the other one is what? How would,
False and not false.
2. False and not false. Oh, I think this is the same kind of thing. Because here we have the identity.
No,
Oh,
0.
oh, you're right, it's the 0. Yeah, it's the 0.
So it's false.
0 of and, which is 3 point what?
3.4. 0.
3.40?
Yeah.
I'm just taking your word for this.
And it's just false. Anything and false is false.
Oh, anything and false is false. Is that what we were trying to prove?
Yeah.
Oh, and that's it?
That's the other side. Is
One stepper? Cool. All right. So there you have the story of case analysis. See you all on Monday.